In this lesson, you will learn how control laws protect a modern fly-by-wire aeroplane's flight envelope, and how similar protections are provided in a traditional aeroplane with the autopilot engaged. You will also learn the definition of a control law and the different flight envelope protections available. If you examine the setup on a non-fly-by-wire aircraft, you can see that the pilot input directly commands a deflection of the control surface. So no matter what input the pilot puts in, the control surface will move in direct proportion to the input and could overstress the aircraft. To maintain a desired flight path, a pilot constantly adjusts the controls. If we now compare this with a fly-by-wire aircraft, it can be seen that any input from the pilot directly orders an aircraft response through the flight control computer. So no matter what input the pilot makes, the computer will only allow an appropriate response to the flight controls. The computer maintains the flight path the pilot has selected and also ensures that the aeroplane cannot be overstressed. The relationship between the pilot input and the control surface movement is called control law. Fly-by-wire control laws are divided into various categories based on aircraft serviceability and stages of flight. The first is normal law, which is applied when all systems work or when a single failure of a computer or a peripheral system is experienced. Alternate law applies when multiple failures of redundant systems are experienced. Direct law is applied when certain multiple failures are experienced. With an autopilot engaged in a traditional aeroplane, similar flight envelope protections are provided. There are two further occasions when normal law is not applied, and these are during ground operation and flare mode, when the normal pitch laws would be unsuitable for safe and instinctive pilot operation. The purpose of flight envelope protection is to give a pilot full authority, in order to consistently achieve the best possible aircraft performance in extreme conditions and to reduce the risks of over-controlling or overstressing the aircraft. The system provides protection in all phases of flight to prevent exceeding the limits for the following parameters: angle of attack, high speed, pitch attitude, bank angle, and load factor. There are certain circumstances when a high angle of attack is desirable, like ground proximity or wind shear, to name two. In conventional aeroplanes, under these circumstances, pilots are advised to pull the nose up until they reach stick shake and maintain this attitude. For a pilot to maintain the ideal flight path is not easy. Pull back too much and the aeroplane enters a stall. Not pulling back far enough would not achieve the best climb angle. Either situation would lead to an accident. But with a fly-by-wire system, the pilot can pull back fully on the controls and the flight control computer will ensure that the aeroplane achieves the best angle of attack without stalling. It achieves this by allowing the angle of attack to increase until the aeroplane reaches alpha prot, where the pilot demand is converted into an angle of attack demand. If the pilot continues to pull back on the control, the aeroplane will continue to increase its angle of attack and the auto throttles will apply more power. If the pilot is still demanding an increase in the angle of attack, the flight control computer will allow him to select up to alpha max and no more. If the pilot was to release the control at any stage above alpha prot, the computer would maintain alpha prot angle of attack. Maximum speed of the flight envelope is defined by velocity maximum operating, VMO, or Mach maximum operating, MMO. In a descent, if the speed increases above VMO, MMO, and the controls are in neutral, the aeroplane will pitch up. To reduce the speed below VMO, MMO. If the controls are demanding a descent, then the speed excursion beyond VMO, MMO will be larger. The aeroplane will again pitch up and maintain a speed slightly above VMO, MMO. Pitch attitude protection enhances the angle of attack protection and high-speed protection by limiting the maximum pitch angle to 30 degrees nose up and 15 degrees nose down. On commercial aeroplanes, the bank angle does not normally exceed 30 degrees. For an Airbus aeroplane, if the bank angle remains within 33 degrees, the flight control computers will automatically apply pitch compensation and maintain the selected bank angle when the controls are released. The pilot can select up to 67 degrees. However, outside 33 degrees, no pitch compensation is applied. And if the controls are released, the bank angle will be reduced to 33 degrees. Turn coordination is provided throughout the whole bank angle range. Load factor is the amount of G being applied to an aeroplane at any one time. G varies depending on the manoeuvre being undertaken. In a banked turn, we use part of the lift vector as the turning force, and therefore need to increase the G-force to maintain level flight. For example, in a steady-state 30-degree bank turn, the aeroplane undergoes a G-force of 1.15 G. Whereas at 60 degrees bank, the G requirement is increased to 2 G. In conventional aeroplanes, remaining within the aeroplane's load factor requires pilot judgment and feel. In an emergency, this could lead to the maximum load being exceeded and damage to the aeroplane. In a fly-by-wire aeroplane, the flight control computers know the instantaneous G load, which is supplied by accelerometers, and will reduce the elevator input to remain within the aeroplane's load factor limit. In this lesson, you have learned about fly-by-wire control laws and the flight envelope protection system. The most important thing you need to remember is that the relationship between the pilot input and the control surface movement is called control law.